Today we're going to talk about u-substitution, which is a method we've used before, but now we're going to apply it to exponential functions or exponential equations. So what we do with u-substitution is we identify an expression that appears in the problem multiple times. Something complicated. We won't use this most of the time, but if there's something complicated that happens in the problem multiple times, you might want to try u-substitution. Define that expression to be u, and if you need to, sometimes you'll need to manipulate, like multiply, square, do something to u to get other parts of the problem. Then you substitute in order to eliminate the original variable and only have u in your equation. Then you solve for u. Once you have your solutions for u, you use those solutions to solve for the original variable. This becomes clearer once we do an example. So when I look at this problem, it's kind of annoying, and I notice that 1 over x minus 1 appears multiple times in the problem. Well, it only really appears here, but there's something similar to it that appears here. If I square it, I get 1 over x minus 1 squared. Or if I double that, I get 2 over x minus 1 squared. So now I can use these definitions to say 2u squared plus u equals 6. And this is an equation we know how to solve. So let's see, 2u squared plus 4u minus 3u minus 6 equals 0. 2u u plus 2 minus 3u plus 2 equals 0. So 2u minus 3 u plus 2. So we have two solutions. For u, we have u equals 3/2 and u equals -2. Now we can substitute those back in. Since those are our u values, we can say that 3/2 equals 1 over x minus 1, and our other solution will come from -2 equals 1 over x minus 1. So we solve both of these equations, cross multiply, equals 2. So 3x minus 3 equals 2. 3x equals 5. X equals 5/3. And then our other solution, -2x plus 2 equals 1. -2x equals -1. And x equals 1/2. So that is one way to solve this problem. Now this particular problem could be solved without u-substitution, but this breaks it into two problems that we definitely knew how to solve from Algebra 1 material, just solving quadratics and solving proportions. Let's do some more examples. This problem might have has a clear thing that is weird about it. I'm going to set u to be t minus pi squared. So that means that this is t minus pi squared. If we square that, we get t minus pi to the 4th. So now we can substitute that in. So u squared plus 2u equals 8. U plus 4, u minus 2. So u equals -4 or 2. Now we can substitute that back in. So -4 equals t minus pi squared, or 2 equals t minus pi squared. Square rooting both sides gives plus or minus 2i equals t minus pi. Adding pi plus or minus 2i equals t. And then this one, plus or minus the square root of 2 equals t minus pi. Pi plus or minus the square root of 2 equals t. So this method got us our four solutions much easier than having to do something strange with this. I mean, we have an irrational part that's real and a complex part. You would much prefer using this solution method than trying to find rational roots or something like that. I mean, you're not even going to succeed with rational roots because none of the roots are actually rational. U-Substitution, very valuable, recognizing that t minus pi squared is a common part of this problem. One last one, and why I brought it up in the exponential functions unit, is to see 5 to the 2y minus 3 times 5 to the y equals 70. What's the most annoying part of this problem? Well, it's the 5 to the y. So I'm going to call u equals 5 to y. How do we get 5 to the 2y out of that? Well, once again, it's squaring it. This is the same thing as 5 to the 2y. So now we have u squared minus 3u equals 70. So what is this? U minus 10, u plus 7 equals 0. So u equals 10 or negative 7. Substituting back in, we have 10 equals 5 to the y, or negative 7 equals 5 to the y. This part has no solution. If we took the log base 5 of both sides, we'll be taking a log of a negative, so that's no solution. And if we take the log base 5 of here, we have log base 5 of 10 equals y. So that is our solution. So when you notice that you don't want to use a u-substitution for every problem, but when you notice that there's something complicated happening multiple times in the same problem, you can use u-substitution to make it an easier problem.